You may remember that we discussed the revelation in the 1700s that isolated systems do not gain or lose mass when they undergo a chemical reaction. Lavoisier, Dalton, and many others used this law of conservation of mass as a foothold to begin unlocking some of the most fundamental concepts of chemistry, like atomic theory. Now, when we draw out a chemical reaction, we're indicating how a system changes as bonds form and break. So it stands to reason that if the atomic theory and conservation of mass are in fact scientific laws, then my depiction should honor that, having no atoms created, destroyed, or modified in the change that I'm trying to show. This is the inspiration for placing a coefficient before each species in my reaction. The coefficients of all reactants and products are carefully chosen to ensure that an equal number of each kind of atom appears on both sides of the equations. We call this relationship, the molar ratios of each reactant and product involved in a given reaction, a reaction's stoichiometry. When the coefficients properly account for this, we call a chemical equation balanced. Balancing equations is a crucial skill, nearly as old as the science of chemistry itself, and indispensable even in the most modern laboratories for reasons that we'll soon see. Now, balancing most chemical reactions relies on one very, very important rule, and that is that reactions must be mass balanced. In other words, the same number of atoms that go in of each kind must come out at the end of the reaction. Recall, this was a critical rule in Dalton formulating his atomic theory. And we looked at a reaction between oxygen and hydrogen when we had that discussion. And remember that when one molecule of oxygen and one molecule of hydrogen reacted, we were able to form hydrogen peroxide. And more recently, we learned how to write this using chemical notation. This reaction would be O2 plus H2 goes to H2O2. Now, I've left the phases out in this case because it's not of consequence to us balancing the reaction. Now, in this case, it was very handy because if we take an inventory of all the atoms that are involved in this reaction, take a look over here at our reactants. We have one oxygen molecule that has two oxygen atoms, one hydrogen molecule that has two hydrogen atoms, and assuming that those coefficients are 1, gives us an inventory of two oxygen atoms, two hydrogen atoms. Taking a look over here at our product side of the reaction. Again, assuming that it has a coefficient of 1, leads me to an inventory of two oxygens and two hydrogens. So this is a very simple reaction for us to balance because all of the coefficients are 1. We're not always going to be that lucky, though. Take an example of the other reaction that we used during that discussion about Dalton's atomic theory. We took a molecule of oxygen and then we reacted it with two hydrogens. Now, in this case, oxygen and hydrogen can be combined in order to make water. But in this case, the ratios aren't as simple. So let's take a look at the reaction between oxygen and hydrogen to form water without the benefit of knowledge of exactly what those ratios are. And ask ourselves, could we simply look at this reaction and tell exactly what the coefficients have to be? Well, we can. And in order to do it, we have to take that inventory of atoms again, assuming at first that we have all coefficients of 1 all throughout the reaction. So when I do this and I take my inventory of oxygen and hydrogen, what do I see? Well, over here on my reactant side, looks like I've got two oxygens, and I've also got two hydrogens. But over here on my product side, something's changed, right? Now I have H2O. And 1 mole of H2O would have only 1 mole of oxygen and 2 moles of hydrogen. So I can't leave the equation this way. This chemical reaction is not balanced. I can't have atoms spontaneously appear or vanish. They've got to be accounted for on both sides. The way that we go about this is, of course, by changing their coefficients to make sure that we achieve that mass balance. But there are some important tricks to getting it done as quickly and concisely as possible. And the most important one probably is this: lock up those pure elements. Leave them alone until the very end. Changing the coefficients on oxygen and hydrogen will only change the amount of those particular atoms on either side. But when I change coefficients on water, I'll be changing multiple atoms. So I'm going to begin with water, and then I'm going to fine-tune my balancing using those elements. So water is all I have left. Let's think about this for a moment. If I've got only one oxygen atom in my inventory here, on my product side, but I've got 2 on my reagent side. How can I fix that using a coefficient? Well, of course, I changed water's coefficient to 2. Now, in doing so, I changed the amount of oxygen atoms to 2, but I've also thrown my hydrogen out of balance now. Now I have 4 hydrogen atoms in my products. But I have an ace in the hole here. I have a way to change the hydrogen accounting without messing anything else up, right? All I have to do is unlock those elements and start using them. So my hydrogen has a coefficient of 1 now. By changing that to 2, I can change the number of hydrogens on the reagent side to 4. Now I have a balanced equation. Let's try something a little bit more complicated. Another reaction that we've seen before, the combustion of propane. Here's the combustion of propane without coefficients. C3H8 is our propane, O2 is our oxygen, CO2 and water are our products. Now in this case, I've got 3 types of atoms, so I'm going to have a bit more complex of an inventory here. On the reactants and product side, I'll have carbon, hydrogen, and oxygen. Let's figure those out, assuming that I have coefficients of 1. Well, I have 1 propane with 3 carbons in it, so I have 3 carbons on my reactant side. Over here I've got 8 hydrogens, and I have 1 oxygen molecule giving me 2 atoms of oxygen. How about on the product side? Well, a mole of CO2 gives me 1 mole of carbon. A mole of H2O gives me 2 moles of hydrogen, and the 2 combined, right, give me a grand total of 3 of oxygen. So we've really got our work cut out for us now, don't we? Nothing is balanced. Now, the next step in the process, remember, is lock up those elements. Don't change them until the very end. Now we can start balancing various elements at will. Let's start by changing carbon in CO2 by changing its coefficient to 3. By tripling the magnitude of that coefficient, I'm going to triple the amount of carbon, but I'm also going to add additional oxygens, in this case 4 more oxygens, a total of 6 oxygens coming from CO2. So I've managed to balance carbon, but I still have 2 elements to worry about. So let's go to water and try to use water to balance out the hydrogen. Right? Notice that we are deficient in hydrogen over here on product side, and I've only got 1 source of hydrogen on the product side. So let's increase that. I'm going to increase the coefficient to 4. And in doing so, I'm going to increase the amount of hydrogen to 8, but I'm also going to add additional oxygen atoms, bringing their total to 10. So carbon is balanced. Hydrogen is balanced. Oxygen is still not balanced, but I've got that ace in the hole. Remember, I've locked up that oxygen and not tinkered with it yet, because now I can change it, and in doing so, only alter that last ratio that's not quite right. So to get the same number of oxygens on both sides, I simply change my coefficient on oxygen to 5, giving me 10 oxygen atoms. Now I have achieved balance, and now we can see how we can determine exactly how much oxygen will react with exactly how much propane without ever running the reaction itself. All we have to know is the reactants, the products, and how to properly balance the reaction. So we've concluded balancing the chemical reaction for the combustion of propane. But to what end? Where's the utility? After all, when we work in the lab, we don't sit at a microscope with tweezers counting out numbers of molecules. Not only is that essentially impossible because of the scales involved, but just imagine how long it would take to count out a mole of molecules. Heaven help you if you lose count and have to start over. No. In the lab, we like to measure in observable units, like mass and grams, for example. So it might seem at first like there's a problem here. You and I measure quantities of reactants in grams, but the reactions themselves are governed by ratios of molecules themselves. But molar masses give us a way to navigate the gap between mass and number. And now that we have stoichiometry, we can analyze the economics of chemical reactions. What do I mean exactly by economics of reactions? Well, one of the great uses of balanced chemical equations is in their ability to tell us how much of each chemical we need to complete a reaction on a given scale. Just like the manager in an automobile factory can determine how many cars can be made that day based on how many tires, steering wheels, and engines are in inventory, or a chef working in a kitchen can inventory his or her ingredients for making bread and predict the day's maximum output. So can a chemist determine just how much of a particular compound can be consumed or created based on the availability of other reagents in a chemical reaction? When we have a reaction taking place between two or more reagents, the question always comes up, which will run out first? This is important to know, potentially for several reasons. We don't want to be wasteful with expensive materials, for example. Having leftover pricey materials at the end of manufacturing makes for bad business, and chemistry is no exception. Also, whichever is completely consumed first will dictate not only how much of the other reagents remain at the end of the reaction, but the maximum amount of product that can form as well. So we want to be able to determine and predict how our chemical ingredients will come together if we're going to run our reactions with the utmost of economy. We call this reagent, the one that we expect to be depleted first, the limiting reagent for a given reaction. And the amount of a product that can be produced by its complete consumption is called the theoretical yield of a reaction. So let's think about how we can determine the limiting reagent and theoretical yield of a reaction using our balanced chemical equation from earlier. Recently, we took a look at this reaction. Right? We looked at the combustion of propane with oxygen, and we balanced the equation. So let's use that balanced equation now to answer a question. And the question is this. When a gram of propane reacts with 2.5 grams of oxygen, which one is consumed first? Interesting question. How are we going to figure this out? I've given you information here in grams. These are quantities that we can measure in the laboratory. But the reaction is balanced in moles. So we've got to find a way to jump back and forth between these values we can measure in the lab and the values that the balanced reaction gives us. Well, here's how we go about that. Here's our balanced equation that we determined previously. Now, when 1 gram of propane reacts, the question we need to ask ourselves is, how much oxygen would that gram consume? Right? And then ask ourselves, do we have enough? So, a gram of propane isn't going to do me much good when all my coefficients here are in moles. But I have a way of getting from grams to moles, the molar mass. So, my target being grams of oxygen, keeping that in mind, I've got to go through the stoichiometry first. I've got to go through that molar quantity. So I'm going to use the molar mass of propane, which I've estimated at 44 grams per mole. But notice that I have divided through by that value because I want grams of propane to cancel. Now I'm dealing with moles. That's great, because my reaction stoichiometry tells me that 1 mole of propane is going to react with 5 moles of oxygen. And I can use that as a conversion factor, setting it up such that moles of propane will cancel. Now I'm working with oxygen, so I'm on my way. But again, this is moles of oxygen as set up, and I want to know how many grams, because I'm working in the lab where I can weigh things out. So to make that final conversion, I'm going to use the molar mass of oxygen, which I've estimated at 32 grams per mole, and placed into the equation so that units cancel, leaving me with grams of O2, the quantity that I want. This calculation tells me that a gram of propane is going to need 3.64 grams of oxygen in order to completely react. So, is oxygen limiting in this case? Well, the problem gives me 2.5 grams, but I now know that I need 3.64 grams, and because that quantity is less, I now know that my oxygen is in fact limiting. It will run out before the propane does. Now that we've determined which one of our reactants is limiting, let's put that knowledge to use and determine what we call a theoretical yield. And to determine our theoretical yield, we're going to use the same quantities. Let's say that 1 gram of propane is going to react with 2.5 grams of oxygen, and I would like to know how much water will that reaction produce. Now, of course, the first piece of information I need is that limiting reactant, which we just discovered is actually the oxygen. So I'm going to use my reaction knowledge and the knowledge that oxygen is limiting to calculate that. So again, I'm going to begin with 2.5 grams of O2 because this was my limiting reactant. It's going to run out first and stop the reaction when it's consumed. The question I'm asking is, how many grams of water can we form from the reaction of 2.5 grams of oxygen? So, keeping my starting and ending points in mind, let's set up an equation using our knowledge of molar masses and stoichiometry to get to the answer. I'm going to use the molar mass of oxygen first to get out of the realm of grams and into the realm of moles to use my reaction. So I'll estimate that at 32 grams per mole, and be sure I divide through because I want those units to cancel properly. So now we're dealing with moles. We're on our way. The next step is to include the reaction stoichiometry. In this case, because I properly balanced the reaction, I know that 4 moles of water are going to be produced when 5 moles of oxygen is reacted in a combustion reaction with propane. So here I place them into this term in such a way that moles of oxygen cancel. Now that I'm dealing with water, I want to get out of the realm of moles and back into grams. And to do that, of course, we're going to use water's molar mass, estimated at 18 grams per mole, and insert it into the equation in such a way that moles of water cancel, leading me to the unit that I want, grams of water. All that's left to do now is grab that calculator and run the math. And when I do this, I discover that 1.13 grams of water will be produced when 2.50 grams of oxygen reacts completely in a combustion with propane. If I wanted to validate this or verify this, I could simply run the same equation using my gram of propane, setting up all of my terms so that I have appropriate canceling. If an entire gram of propane were to combust, that would actually produce 1.64 grams of water. Again, a validation of our selection of oxygen as a limiting reagent. This reaction will run until 1.3 grams of water is produced, at which time the oxygen will be fully consumed and the reaction will stop. So we were able to use a balanced chemical reaction to determine not only that oxygen is limiting in our case, but that exactly 1.13 grams of water should form if the reaction runs perfectly and to completion. As you might expect, things in the lab rarely go perfectly. Some reactions don't run all the way to completion. Others lose product mass to unwanted side reactions that produce what we would call byproducts. Any number of things can cost us a portion of our product. So chemists often report the yields of their reaction as a percentage of the theoretical yield. This is done easily by taking the actual yield of a reaction, dividing it by the theoretical yield, and multiplying by 100% to convert it into a percentage. For example, if our combustion reaction was found to produce 1.0 grams of water, that would be our actual yield. Compare this to the theoretical yield, and we see that we actually obtained 88.5% of what the theory tells us we could obtain. If you pick up nearly any synthetic chemistry journal and open it to just about any article, you will see reaction yields often reported in this way. But stoichiometry isn't just about deciding which reagents are present in excess and which ones are limiting. Sometimes, scientists and engineers need to create systems which use reactions in which just the right amount of all reagents are used, so that when the reaction is complete, all the starting materials are consumed, leaving none at all behind. A perfect example of this is a chemical reaction used by NASA to keep its astronauts alive on early space missions. You see, to keep alive, you and I, and every human being for that matter, have to breathe. So naturally, NASA sends plenty of oxygen along with its manned vehicles to be sure that nobody suffocates during a mission. I would call that a sound policy. But just having enough oxygen isn't the only concern when it comes to the breathing of astronauts. Although we have to take oxygen into our bodies to survive, our bodies use that oxygen and then expel carbon dioxide as a waste product. Now, there's a very good reason that we exhale that carbon dioxide because it's toxic to us at fairly low levels. Here on Earth, this is not typically a concern to us because that exhaled carbon dioxide is carried away by circulating air and eventually it's consumed by plant life and other sinks in the environment in part of what's called the carbon cycle. It all works in perfect balance, giving us an environment in which we can comfortably breathe indefinitely. But when you place a small crew of people into a tin can and shoot them into space, effectively isolating them from the natural carbon cycle, things change. In the confined volume of a spacecraft, carbon dioxide accumulates to toxic levels very quickly, and carrying a small forest along for the ride to help consume it, as happens here on Earth, simply isn't feasible. So scientists at NASA developed canisters that use a chemical reaction to consume the carbon dioxide. The reaction involves the reaction of lithium hydroxide, with the CO2 in the atmosphere to create harmless lithium carbonate and water. Having enough lithium hydroxide is crucial, but launching excess material into space is very costly. So a NASA engineer from this time would be faced with a real challenge. Send up enough, but just enough lithium hydroxide to keep your crew alive. Now this is the reaction, right? CO2 plus lithium hydroxide reacts to form lithium carbonate and water vapor. But I've got to balance this reaction first, because if I'm going to get my quantities right, I'm going to have to do another one of those gram to mole to gram conversions. Now our atom inventory will include lithium, carbon, hydrogen, and oxygen. Looking at my reactant side of the equation, as written, right, assuming they're all coefficients of 1, I have 1 lithium, right, I have 2 on the other side. I'll have 1 carbon on my reactant side and 1 on the products. Over on my reactant side, I currently have 1 hydrogen, whereas my products, having water, has got 2. And oxygen on my reactant side right now counts up to 3, whereas on my product side, I'm looking at 4. So we're not balanced right now. To assume that 1 mole of CO2 reacts with 1 mole of lithium hydroxide may not be correct, and we need to be correct here. So let's balance the equation. First thing is we're going to look for pure elements that we can lock down. We don't have any. So at this point, all we can do is start looking for discrepancies in the atom inventory and correcting them. We'll start at the very top. I have 2 lithiums from my lithium carbonate formula on the product side and only 1 lithium currently from the lithium hydroxide on my reactant side. So to correct for this, I can simply change the coefficient on lithium hydroxide to 2. This brings lithium up to 2. This also brings hydrogen up to 2. And it adds another oxygen, bringing that up to 4. So we've completed balancing this equation at this point by increasing the coefficient on lithium hydroxide to 2. Now it's time to get down to the business of determining exactly how much lithium hydroxide it takes to keep one of our astronauts alive for a day. Now to do this, I'm going to use the assumptions from the problem. That 900 grams of CO2 will be exhaled by that person in 1 day. That's how much starting material I have. And I want to know exactly how many grams of lithium hydroxide will it take to be absolutely sure that the CO2 is limiting. Right? What's the minimum amount of lithium hydroxide I need to be sure that all of that CO2 is consumed? Well, again, I'm going to have to get to moles because I'm using reaction stoichiometries here. So, having grams of carbon dioxide, I want to use the molar mass of CO2, which I've estimated at 44 grams per mole, plugged into the equation in such a way that grams of CO2 will cancel. Now I'm in the world of moles. That's good because I can use that new reaction stoichiometry. And remember, balancing the equation told me that it's going to take 2 moles of lithium hydroxide to react with 1 mole of CO2. Place that into my equation and cancel moles of CO2. Now that I'm in units of lithium hydroxide, I want to switch back out of the world of moles and into the world of grams, which I can actually use in manufacturing a product in a laboratory somewhere. And for that, I'll use the molar mass of lithium hydroxide, which I've estimated at 24.0 grams per mole, plugged into the equation so that moles of lithium hydroxide cancel. This should give me the correct answer because my unit analysis tells me so. Plugging these numbers into my calculator, I get 982 grams of lithium hydroxide. So it takes just about 1 kilogram of this material to keep one person alive inside of a space vehicle for 1 day. Using stoichiometry and a little bit of ingenuity, the engineers and scientists at NASA could determine exactly how much lithium hydroxide is needed to complete the critical reaction with CO2, ensuring the safety of the crew, while also helping to be sure that additional weight is not unnecessarily launched into space along with them. And it's all thanks to stoichiometry. Forget that 2 coefficient on lithium hydroxide, and you're coming home early, or maybe not at all. So let's sum up what we discussed today. We started by learning how to balance a chemical reaction, ensuring that the coefficients used in a given reaction lead to proper mass balance. Next, we discussed the concept of the limiting reagent, which is simply the reagent that's expected to be consumed first in any given system. We saw how, in combination with a balanced chemical equation, the limiting reagent can be used to calculate a theoretical yield for any reaction we can imagine. After this, we discussed how things in the real world rarely go as expected based on calculations. So we often report the actual outcome of a reaction as a percent yield, which is simply the ratio of actual to theoretical yields normalized to 100%. Finally, we turned stoichiometry on its head and used a balanced chemical equation to determine exactly how much of one reagent was needed to completely consume another, giving us a way to optimize reactions for use in environments where eliminating waste is crucial. With that, our short introduction to chemical reactions and stoichiometry is complete. It's now time to put those chemical changes aside for a short while and consider another fundamental kind of change which will come to bear on future discussions on the properties of matter. Next up, we're going to discuss the phases of matter and how they interconvert. Stoichiometry, or the use of balanced equations, can be a really powerful predictive tool. So let's explore that a little bit using a challenge problem. Camels. Why not? Camels and other animals in the desert are adapted to use water in a very efficient manner. In fact, camels can store water as fat. Isn't that interesting? So what they do is they use a fat called tristerin. And our question here is, what volume of liquid water can be recovered from the burning of 1 kilogram of the fat tristerin, which camels keep in their humps? Now, the formula is here. It's rather large, but we can still balance this equation and use stoichiometry to get to our solution. So let's get started. Here's my unbalanced equation, where my fat tristerin reacts with oxygen to create carbon dioxide and the water that the camel is after if it's a little bit thirsty. Remember, we have to get our atom inventory going here, with reactants and products both considered. So you'll notice we have 3 different types of atoms here. We have carbon, hydrogen, and oxygen all on both sides of the equations. And if I assume coefficients of 1 for every molecule here, I would calculate that I have 57 carbons, 110 hydrogens, and 8 oxygens on my reactant side. And I currently have 1 carbon, 2 hydrogens, and just 3 oxygens over here on my products. So obviously, we have a lot of work to do. Let's get down to it. Remember, the first thing we want to do here is we want to lock up those elements, right? Pure elements, we do last. Those are our ace in the hole to get the balancing just right at the very end without undoing a lot of the work that we've already done. If I add a coefficient of 57 to CO2, that allows me to balance the carbon, right? But in doing so, that also adds a considerable amount of oxygen, so I have to be sure I accounted for that. So let's see here. What can we do next? Hydrogen. Let's use the water to balance those 110 hydrogens in my tristerin molecule. I'll need 55 waters at 2 hydrogens per water. So now that I've got my carbon and my hydrogen balanced, I can finally unlock that element, oxygen, and use it to finish off balancing my equation without undoing all this hard work. So in this case, I'll need a coefficient of 81.5 for my oxygen to be sure that everything balances out nicely. Now remember, I can use fractional numbers up here because we're talking about moles, not molecules. Now, let's use this balanced equation to answer the question. Question is, if we have 1 kilogram of tristerin, how much water will we get? So we need to know the molar masses of both. And I place those equations here so you can review those. Now we need to use that stoichiometry to get to our answer. Remember, we're going to start with a kilogram of tristerin, which I've chosen to write as 1,000 grams. I know where I'm starting. Now I need to know where I'm going. I'm going towards grams of water. That's the ultimate answer to my question. So I've got some work to do. I'm going to use the molar mass of tristerin placed into my equation in such a way that I will cancel grams of tristerin and get moles. Next, I'm going to use that balanced reaction to create a conversion factor based on the stoichiometry. 55 moles of water for every mole of fat. And finally, I'll use the molar mass of water to be sure that I get the units I want at the end. My unit analysis tells me grams tristerin cancel, moles tristerin cancel, moles water cancel, and my final answer will be in units of grams of water. In fact, 1 kilogram of fat creates 1,112 grams of water, more than a liter. That's a pretty good amount to have a nice drink on a hot day in the desert, isn't it?